Welcome to the TOEFL Listening section. In this section, you will listen to an academic lecture and then answer questions about what you heard. You may take notes while you listen. You will have time to review your notes before answering the questions. Listen to part of a lecture in a university class. You will hear the lecture only once, so listen carefully. After the lecture, you will answer some questions about what you heard. Some questions ask about the main ideas and supporting details. Other questions ask you to make inferences or connections between ideas. Answer each question based on what is stated or implied in the lecture.
Good morning, everyone. Today we will focus on artificial intelligence applications within robotics, with a specific emphasis on machine learning in autonomous systems. I want to show you how learning methods are integrated into perception planning and control, and why that integration matters for real-world robots. First, I will outline three broad roles that machine learning plays in robotics. The first is perception. Deep convolutional neural networks process camera images and combine with sensor fusion algorithms to interpret the environment. The second is decision-making and planning. Reinforcement learning and imitation learning generate policies for navigation and manipulation. The third is model learning. Here, systems identify dynamics or build predictive models that feed into model predictive control or into planners. For perception, a common artificial intelligence application is sensor fusion. For example, combining LiDAR and RGB cameras using a learned fusion layer reduces false positives in obstacle detection. In indoor mapping, simultaneous localization and mapping, or SLAM, has benefited from learned components such as learned feature descriptors and neural loop closure detectors. These learned modules improve robustness in cluttered scenes. Let us consider decision-making. Reinforcement learning gives robots the ability to learn from trial and error. In warehouse picking robots, reinforcement learning has been used to improve grasp selection and motion trajectories. However, pure learning can be sample inefficient, so we often use hierarchical approaches. For instance, a high-level planner may choose a goal, while a low-level learned controller executes stable trajectories. A concrete case study is dexterous manipulation. Open research has demonstrated that a robotic hand can learn to manipulate objects using simulated training combined with domain randomization. Domain randomization exposes the learning agent to many variations in simulation so that the resulting policy generalizes better to the physical hand. This method is a practical artificial intelligence application that enabled success in a task that was previously hard for classical control alone. Another important technique is sim-to-real transfer. Reinforcement learning often requires thousands of trials, which are impractical on a physical robot. We train in simulation and then transfer the policy to hardware. Techniques like domain randomization and system identification reduce the reality gap by randomizing textures, dynamics, and sensor noise during simulation. But there are hybrid approaches that combine classical control with learned models. For example, model predictive control can use a learned dynamics model to predict future states and optimize safe actions. Combining a traditional controller with a learned residual policy often yields better disturbance rejection and safety guarantees than a purely learned controller. In aerial robotics, artificial intelligence applications include learning-based state estimation and adaptive controllers. Drones operating in urban environments use learned perception stacks to detect windows, doors, and power lines. Learning helps with wind disturbance compensation when combined with robust control strategies. Valuation is critical. For autonomous systems, we measure success by task completion, safety margins, and sample efficiency. Safety is a major constraint, so constrained reinforcement learning and reward shaping are common practices. We may add penalties for collisions, or require a safety layer that can override unsafe actions in real time. Let us talk about limitations. Learned policies can be brittle under distribution shift. They may require significant compute and energy, which matters for mobile robots with limited onboard processors. Interpretability is another issue. When a perception module fails, we need diagnostic tools to explain that failure. Finally, I want to highlight promising directions. One direction is better sample-efficient algorithms, such as model-based reinforcement learning and meta-learning, so robots adapt quickly to new tasks. Another is multimodal learning that tightly couples vision, touch, and force sensors. And the third direction is formal verification of learned controllers, so we can provide provable safety guarantees. In summary, artificial intelligence applications in robotics are transforming how robots perceive, plan, and act. By combining machine learning with established control and planning methods, we can build autonomous systems that are more capable and robust. Sim-to-real transfer remains one of the biggest challenges for deploying learned policies on physical robots. That completes my overview. Next class, we will examine a specific reinforcement learning algorithm used for robotic manipulation and walk through its training pipeline.
Listen again to part of a lecture, then answer the question.
Sim-to-real transfer remains one of the biggest challenges for deploying learned policies on physical robots.
This concludes the listening section. For more TOEFL practice tests and study materials, visit spinta.org.